In this video, we'll go through calculation examples involving these three common kinematic equations involving velocity, displacement, and uniform acceleration. A mass initially at rest accelerates in the north direction at 2.5 meters per second squared. Calculate the velocity and displacement of the object after 2 seconds. Okay, so here let's look at what we are given by the question. We're given that initially it's at rest, so its initial velocity u is 0 meters per second. And its acceleration is 2.5 meters per second squared north. We have to calculate the velocity, that is the final velocity, and displacement after 2 seconds. So to calculate the final velocity, given the time, we can use the first equation. The first equation tells us what the final velocity of the object will be given the initial velocity, the acceleration, and the time. So v equals to u plus at. V is equal to the initial velocity is 0 plus 2.5 meters per second squared times by 2 seconds. And this will give me 5.0 meters per second north. Remember, it is important to include both the units and the direction for vector-like velocity. Okay, what about displacement? To calculate displacement, we'll have to look at the second or the third equation here, because only these two contain the variable s, which represents displacement. In this example, we can use both equations, because we're given the initial velocity, time, acceleration, and now we've also calculated the final velocity. Let's use the first equation. The displacement s is equal to the initial velocity 0 times by time, which is 2 seconds, plus half times by the acceleration, which is 2.5 meters per second squared, times by 2 seconds squared. This will give me a displacement of 5 meters north. Again, very important to include the units for vector quantity like displacement. We can also use a third equation. V squared is equal to u squared plus 2as. We know that at the end of the 2-second interval, the final velocity is 5 meters per second to north. So we can do 5 squared is equal to 0 squared plus 2 times by the acceleration, which is 2.5 meters per second squared, times by the displacement, which is what we're trying to find. So if we simplify and rearrange this equation, we'll get 5s is equal to 25. So if we divide both sides of the equation, we'll get s is equal to 5 meters north. So using the two equations, we can arrive at the same answer. A mass initially at rest undergoes a motion with uniform acceleration. After 10 seconds, the mass is 100 meters from its original position. So the 100 meters here is my displacement. Let's call that s. Calculate the acceleration of the mass. So here we know that in the first 10 seconds, the object has traveled a displacement of 100 meters. And we also know that at the beginning of the 10 seconds, its initial velocity was 0 meters per second. So here, the second equation will help us the most, because we want to calculate the acceleration after being given the displacement, s, the initial velocity, and the time. So s equals to ut plus half at squared. S is 100 meters. U is 0 meters per second. Time is 10 seconds plus half a 10 squared. So this is 100 is equal to 50a. A is 2 meters per second squared. So here in the positive direction. Because we are not given whether this is north, east, south, or west, we have to describe the direction in a more generic manner. Calculate its instantaneous velocity at 10 seconds. Instantaneous velocity, by way of review, is the velocity of the object at a specific time, especially if the object has the acceleration. Here, because we know the acceleration and we know the time, which is 10 seconds, we can use the first equation. V equals to u plus at. V is your instantaneous velocity. U here is 0 meters per second plus the acceleration, which is 2 meters per second squared. And the time here we put is what the question is asking for. So if I put 10 seconds here into time, the final velocity v that I calculate is the instantaneous velocity at 10 seconds. If you want to find at any other time, all you need to do is to substitute a different number into the time equation here. So my velocity here is 20 meters per second in the positive direction. A car accelerates at 8 meters per second squared from 20 meters per second to 36 meters per second. Calculate the displacement traveled by the car during this time. So here we're given that the acceleration is 8 meters per second squared. The initial velocity is 20 meters per second, and the final velocity is 36 meters per second. So we're given three variables, a, u, and v, and we want to calculate the displacement. If you look at the three equations, the most suitable one is the third one here, because we're given the final velocity, the initial velocity, and the acceleration, and we want to find the variable s, which is displacement. V squared equals to u squared plus 2as. V is 36 squared is equal to 20 squared plus 2 times by 8 meters per second squared times by the displacement s. So we'll get 16s is equal to 36 squared minus 20 squared. So s is equal to 36 squared minus 20 squared divided by 16. The displacement equals 56 meters in the positive direction. A car initially traveling at 20 meters per second accelerates uniformly to 30 meters per second in 5 seconds. Calculate the displacement traveled by the car during this period. Now, this example is slightly different to the previous one because we cannot use any of the three equations involving acceleration if the question hasn't supplied us with acceleration. So the first thing we have to do before we can find displacement is to first calculate what is the acceleration a. We're given the initial velocity u and the final velocity v, and we know the time taken to change from the initial to the final velocity. So we can use the first equation to calculate a. v equals to u plus at. The final velocity is 30 meters per second. The initial is 20 meters per second plus a times by the time during the interval. So a is equal to 30 minus 20 divided by 5, and this is 2 meters per second squared. So this is my acceleration. Now that I have the acceleration, I can use either the second or the third equation to work out my displacement. So let's use the second equation because the displacement is already the subject of my equation. S equals to ut plus half at squared. The initial velocity is 20, the time is 5 seconds, plus half a is 2 meters per second squared, times by 5 seconds squared. The displacement is 125 meters. Now, because acceleration and displacement are both vectors, we should try to describe the direction as precisely as we can. In this question, they haven't given us any descriptions of the direction, so all we can do is to say that both the acceleration and the displacement are in the positive direction. A mass while moving at a constant velocity of 5 meters per second begins to accelerate at negative 2 meters per second squared. When you're reading this, you should try to visualize the motion of this mass. It has a positive velocity but a negative acceleration. So the direction of the two vectors are in the opposite direction. What does that mean? That means the speed of the object is slowing down. It's decreasing over time. It's going slower and slower as time goes by. Part A asks, after how many seconds will the mass come to a stop? That is, its velocity becomes 0 meters per second. So we can use the first equation because we're given the acceleration, we're given the initial velocity, and we are asked to find time. V equals to u plus at. The final velocity is 0 because the question is asking when the mass will come to a stop, equals to the initial velocity of 5 meters per second plus minus 2 times by time. Minus 2 here is the acceleration. So time is equal to 5 over 2, which is 2.5 seconds. Part B, what is the displacement of the mass at t equals to 10 seconds. So again, we can consider the second and third equation because only these two contain the variable displacement. However, the third equation is a bit more difficult because it requires us to know the final velocity at 10 seconds. And this is something that we are not given and we haven't found yet through calculations. As a result, the second equation here is more suitable because we know the initial velocity of the object at the beginning of the 10 seconds. We know the time, which is 10 seconds. We know the acceleration is minus 2 meters per second squared. S equals to ut plus half at squared. The initial velocity is 5 meters per second. The time is 10 seconds plus half minus 2, 10 squared. So the displacement of the object is minus 50 meters. You can rewrite this as 50 meters in the negative direction. Part C, what is the distance traveled in the first 10 seconds? Now, you might be thinking, what's the difference between question B and question C? Aren't they asking for the same thing? Well, not necessarily. Remember that displacement and distance are similar, but also distinctly different, as displacement is a vector. It is the position of the object from the original starting position, whereas the distance is simply how far the object has traveled, regardless of direction, as it is a scalar quantity. In this scenario, there is a big difference between displacement and distance because the object at the beginning is traveling in the positive direction as indicated by its positive velocity. And then as it decelerates due to having a negative acceleration, it will eventually come to a stop. And we found that this stop happens at 2.5 seconds. And after 2.5 seconds, it continues to have negative acceleration, meaning that its velocity will decrease from 0 to have a more negative velocity. So if I quickly draw a velocity versus time graph, initially the velocity is at 5 meters per second, and it takes about 2.5 seconds to reach 0. So this is t equals to 2.5 seconds. And due to its negative acceleration, it will continue to decrease in velocity for the remainder of the journey. So over here, let's say this is t equals to 10 seconds. So for the first 2.5 seconds, it's traveling in the positive direction, and then it comes to a stop. Afterwards, its velocity becomes negative, suggesting that it has turned around and now it's traveling in the negative direction. So it's going backwards. Over this time, the distance will always increase, but then the displacement will start to decrease at the 2.5 second mark because the mass has turned around. It's heading back to where it started from. So minus 50 meters, which is what we calculated, is actually not the distance. It's actually the position of the object from the beginning. So to calculate the distance, we need to consider the speed of the object regardless of where it's traveling, whether it's positive or in a negative direction. The best way to do this is to consider the two intervals separately. So we should calculate the distance traveled in each of the intervals separately. Let's calculate the distance traveled in the first interval first. In the first interval, the displacement of the object is given by s equals to ut plus half at squared. So the initial velocity is 5 meters per second, time is 2.5 seconds because that's the length of the first interval, plus half times by minus 2 times by 2.5 squared. This gives me a positive displacement of 6.25 meters. Now in this case, this is also the distance traveled by the object because during the first 2.5 seconds, the object hasn't turned around. It hasn't changed its direction. It's still going in a positive direction at 6.25 meters. It is only after this point it turns around and starts heading back to its original starting point, which would then decrease the displacement. So because the object hasn't turned around during the first 2.5 seconds, the displacement and the distance are equal. So I'll use the variable d to represent distance. In the second interval, which is when it travels with a negative acceleration, we can also use s equals to ut plus half at squared to calculate its displacement. So in this case, the initial velocity u is the velocity at the beginning of the second interval over here. And we know that this is 0 because the object is at rest or comes to a stop at 2.5 seconds. Now the time is the duration of the second interval. This is not 10 seconds anymore, but rather from 2.5 to 10 seconds, this is 7.5 seconds. So times by 7.5 seconds plus half times by a, which is still minus 2 meters per second squared, times by 7.5 squared. This gives us minus 56.25 meters. So this makes sense because the displacement is now negative as the object is traveling in a negative direction due to its negative velocity. But we want distance. So distance traveled during the second interval is plus 56.25 meters because the distance does not account for the direction. Now, to calculate the total distance, we simply add the distance from the first interval to the distance traveled in the second interval. So that's 6.25 plus 56.25. And this gives me a distance of 62.5 meters. During its launch from Earth's surface, a rocket accelerates uniformly to reach 12,000 meters per second in 5 minutes, and maintains the constant speed for another 60 minutes. What is the displacement of the rocket? So this question involves two different types of motion. The first type of motion involves uniform acceleration from 0 meters per second to a final velocity of 12,000 meters per second, and that's over the span of 5 minutes. This is then followed by the second type of motion, which is motion at constant velocity or speed without any acceleration, and this lasts for 60 minutes. When you get scenarios that involves two different types of motion, that is one involving acceleration and another involving no acceleration, you need to do the calculation separately. So that's the first one. The first one is with uniform acceleration. So we know that initial velocity is 0, the final velocity is 12,000 meters per second. The time of this interval is 5 minutes, which is equivalent to 5 times by 60, which is 300 seconds. Make sure you convert the time from minutes to seconds because the velocity units are in meters per second, not per minute. We can use the first equation to find out what is the acceleration of the first interval. So 12,000 is my final velocity, equals to 0 plus a times by 300. And a equals to 40 meters per second squared upwards, assuming the rocket is traveling upwards. Now that I've calculated the acceleration, I can then find the displacement by using the second equation, ut plus half at squared. So displacement equals to 0 times by 300 plus half times by 40 times by 300 squared. So this gives me a displacement of 1.8 times 10 power 6 meters upwards. So during this time, the rocket has ascended by about 1.8 million meters. We can also use the third equation to calculate displacement because we know the final velocity of the rocket at the end of the 5 minutes. V squared equals to u squared plus 2as. So 12,000 squared equals to 0 squared plus 2 times by 40 times by s. So s is equal to 12,000 squared divided by 80. And we get the same answer of 1.8 times 10 power 6 meters upwards. Okay, so we're not done yet because this is the displacement of the first interval, the first part with motion that has uniform acceleration. Remember that displacement here also includes the displacement covered in the second part with constant velocity and no acceleration. So the second part is no acceleration motion. To find the displacement in the second part, we simply take the velocity of the object, because it's constant, times by the time for which it travels. So the velocity during this motion is the final velocity at the end of the first interval, at the end of the first 5 minutes. And we said that was 12,000 meters per second, as given by the question here. The time here is 60 minutes, but we have to convert this into seconds because 12,000 here is meters per second. So we'll do 60 times by 60 seconds in 1 minute. And this gives me a displacement of 4.32 times 10 power 7 meters. Therefore, the total displacement is equal to the sum of the displacement from the first two intervals. Now, we can only add the displacements together to find the total displacement in this case because the rocket is heading in the same direction. It hasn't changed direction during the two intervals of motion. So 4.32 times 10 power 7 plus 1.8 times 10 power 6. And this gives me 4.5 times 10 power 7 meters upwards. This concludes the first video on calculations involving uniform acceleration.